Hello, this is Dan Kernler again, and this is part of our Calc 3 sequence. Today we're talking about section 15.8, where we're going to introduce the idea of Lagrange multipliers. This is another technique for optimization. And so we're going to, in this video, introduce the idea, do an example to illustrate it, and then in the next video we'll do two more examples of illustrating that technique. All right, so first let's talk about what this method is. So we're going to introduce this with just an example to kind of illustrate how it works and develop the idea, and then we'll get a process and do an example. One of the problems that we had done before was maximizing the volume of a box. Suppose we know that this box has a square base and the length and girth couldn't exceed 108 inches. So we did this before, slightly different method. What if we try this again, and we're going to do this differently. We're going to guess what the maximum volume is. So what I have below, in this picture here are, now these are actually mislabeled. So these lines are essentially saying, all right, our volume is length times width times height. If we assume it's a square base, we would have, let's see, length, maybe width squared, or what did I do here? Width squared times length. I think that was the variables I used, so I used width for the base, and then length for the length of the box. So what if we assume the volume is, say, 2,000? And I think these volumes are mislabeled. So assume we have, let's say we start with volume equals 2,000. What we'd have then is we'd have the equation W squared L equals 2,000. Or if we solve for L, L is 2,000 over W squared. And that's what this first curve here is. This first curve is assuming the volume is 2,000. And then it jumps up 4,000, 6,000, etc. So you might recognize these. This is what a level curve is, where you have a fixed outcome, a fixed volume in this case, and you are drawing those curves, what those curves would be for different fixed volumes. The shaded blue area represents where the length plus girth is less than 108 inches. So you can see here 108 inches there. And then if we take the whole 108 and divide it by 4, that would be 27. So there'd be no length, and you just have a cardboard square that's 27 by 27. And that would give you your 108 inches. So the blue area is all the area in here is all possible under the constraints. And then again, you have V equals 2,000, 4,000, 6,000. So what I want you to do is take a moment, pause the video, and put a little dot on the graph here where you think the volume will be maximum. Now, your dot has to be in the blue area or on the edges, because that's the possibility that gives you still the 108 inches. But I'd like you to put a dot where you think the volume is maximum. So pause the video. Why don't you try to do that? Okay. So the key here is the volume keeps increasing with each level curve. So we want to be as far out as possible, which would put us right about here. That would give us that maximum volume. Okay, now here's the second big thing. What is going to be true about the level curve and this constraint here? This constraint is when the length plus the girth, which would be 4W, is equal to 108. So what would be true about them at that point? The key is that the constraint and the level curve are parallel. The constraint and the level curve are parallel. So what does that mean if they're parallel? Well, that means that the gradient is always orthogonal to it, so that their two gradients will also be parallel. So the gradient of V will be parallel to the gradient of the constraint. And this is the key. This is the key. If we let our constraint, let's say here, oops, sorry, did not mean to do that. Let's let G be equal to L plus 4W minus 108. So that's essentially when our constraint is equal to 0. We want the gradient of V to be parallel to the gradient of G, which means it's some scalar multiple. So we'll use lambda as our scalar multiple. Oops. Scalar. So this is the key. This is the Lagrange multiplier strategy. Doesn't seem very helpful right now, but this is the key. The key is to assume that the gradient of your function you're trying to optimize is a scalar multiple of the gradient of your constraint. The key is then we're going to make a guess for V. All we're really doing is choosing level curves. That's the idea. And we're trying to find the level curve that gives us the biggest volume in this case. So here is the process. So the method of Lagrange multipliers, you're going to simultaneously solve the equation where the gradient of your function you're trying to optimize is a multiple of the gradient of your constraint function, and then you also have your constraint function, and you'll be able to use that to solve the system that you end up with. There are some constraints here. This will exist if G and F both have continuous first partial derivatives, and if your function f does have an extremum, as long as the gradient of g isn't 0 there. So that's the situation. So let's try an example here. This is a little bit different from the previous one, but let's actually, from what we did in the previous section, but let's actually try this here. This is the one we're going to assume that the width and height are always equal, and we're going to try to maximize the volume. So the volume again would be length times width times height. We're going to assume width and height are equal, so this is length times w squared. So now volume is a function of length and width. And then we also have our g of L and w. And you can do L plus 4w. You can do that. You can do minus 108 equals 0. It doesn't really matter. Because you're going to be finding the gradient of that. So where the constant is, if you look up in the method above, you just have only a constant on the right-hand side because you're going to find its gradient. And so those derivatives would be 0 regardless, as long as that's a constant. Okay, let's find the gradient of V. That'll be the partial derivative with respect to L, which will be w squared, and then the partial derivative with respect to W, which will be 2LW. And then the gradient of G, partial derivative with respect to L will be 1, partial derivative with respect to W will be 4. And so what we're going to do is we're going to set the gradient of V equal to some multiple, lambda, times the gradient of G. So that means W squared is some lambda times 1, and 2LW is some lambda times 4. And the typical process we do here is actually solve for lambda on both of these, because they both have to be true, right? We have a system, which seems weird. How do we have a system of 2 equations and 3 unknowns? But here's the typical process we do. Solve for lambda. So lambda will be w squared. Here lambda, if we divide by 4, will be 1/2 LW. And so we set those equal to each other. W squared equals 1/2 LW. Now you might say, okay, that's great. Now I have one equation. But remember, you also have the original constraint. So now what we have is we have a system of w squared equals 1/2 LW, and we have L plus 4W equals 108, or L plus 4W minus 108 equals 0. Either way you want to do it. I don't know how we want to solve that. It's kind of up to you. We could do substitution, I guess. L is equal to 108 minus 4W. So W squared equals 1/2 times 108 minus 4W times W. Well, let's see, w squared equals, what is, let's see, 1/2 w, multiply that in there, that would be 54w minus 2w squared. So 3w squared equals 54w. I guess I should have done 3w squared minus 54w equals 0. Factor out a 3w, we get w minus 18 is equal to 0. So w is equal to 0 or 18. Now clearly w equals 0. Yeah, that's a critical point, but it's not going to be relevant for our question. So w equals 18. The length will be 108 minus 4w, which will be 108 minus 4 times 18. 4 times 18, 72, so the length will be 36. So again, if we assume the box is square, which we didn't before, we actually proved that was true with the other technique. Here we had to assume it was true, but if we assume the box is square base, then it's 18 inches by 18 inches by 36 inches. And that is the method of Lagrange multipliers. Let me go back up here and kind of highlight the strategy. So this part right in here is the key to the Lagrange multiplier strategy. That's the key where we set the gradient of our function we're trying to optimize equal to a scalar multiple times the gradient of our constraint function. Okay, that's it for this video. Next video, we will do 2 additional examples, and hopefully by the end of that, you'll have a good handle on what the Lagrange multiplier method is.